Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today's video is about the lesson number 2, static. In the first lesson, we talk about some concepts and definitions of statics. And these concepts and definitions are very important, understanding of them in order to solve static problems. One of these concepts that I leave it for today is concepts of particle. That's a core concept. Particles is a body with negligible dimensions. When dimensions of a body are irrelevant to the description of its position or its motion, we consider it as a point that its mass is concentrated at this point, which we call the point mass or particles. Imagine that we are going to consider or analyze the motion of moon in the Milky Way galaxy, and dimension of moon has no effects on this analysis. With this approximation, we consider moon as a particle. And when we go further in static and solving problems and talking about the forces that acting on one point, sometimes we consider the body as a particles in order to solve the problem and make the problem simpler. Okay, let's start today with vectors. After this concept of particles, let's go to vectors. Previous lesson, we talked about vectors that have magnitude and direction, and we show them with a line segment, that the length of the segment, line segment, is considered represent the magnitude of the vector, and it has an arrowhead that show its sense, represent the sense of the vector. And we talk about 3 types of vectors: free vectors, sliding vectors, and fixed vectors. Today, we consider free vectors to talk about addition and subtractions of vectors. Let's start with vector A. For example, if we have vector A, we show it like that. This is the tail of vector, and this arrowhead is the head of the vector. The tail of a vector, head of a vector, length of a vector, magnitude of a vector. We show, if we write a arrow above it, it means vector A. If I show only A, letter A, it means that this is the magnitude of vector A, only magnitude, has no sense. Sometimes magnitude can be shown by this symbol as well. The vector inside the this sign. Okay. Most of the time we use this method to show the magnitude of vector. If we wanted to show the vector, we show this one. Letter, that arrowhead is above it. Okay. Then let's go for some definition. Another definition here, which is important in static, is unit vector. Unit vector is a vector that its magnitude is equal to 1 unit of length. 1 inch, 1 meter, 1 millimeter, 1 centimeter, 1 foot, just a unit. It depends on the unit of the length in that session. Okay, how we show unit of a vector? The unit of a vector, we can show it here. Magnitude is equal to 1, and we show, for example, EA. EA is a vector with arrowhead above it. It means that the unit vector of A. Unit vector of A has the sense of vector A, the same direction. The only difference is that length of the unit vector is equal to 1. If I wanted to show its magnitude of the unit vector A is equal to 1. That's the definition of unit vector. Any vector has its own unit vector. And important unit vector, actually, when we consider the vector in a system of coordinates in 2D, for example, x, y coordinates. Then in x direction, we have a unit vector. In y direction, we have also a unit vector. Okay, let's talk about after this definition, about the addition of two vectors, parallelogram law and triangle law. Let's consider first triangle law. Assume that we have two vectors A. A is, for example, it's 22, and B, vector B, vector A. We wanted this, assume that these are both are free vectors. Why free vectors? Because I can move them parallel to themselves and bring them on its plane to anywhere else that I wish. Okay, if I wanted to find the addition, I consider a point O and I start from tail A, represent the position parallel to A. I draw vector A parallel to A. This is a free vector. I can move it parallel to itself, to anywhere in space. And then from head of A, I start with the tail of B, head to tail. Then, how much is the magnitude? 8 inches. I draw 8 inches parallel to B, parallel and equal to B. That's vector B. Then if I attach the tail of A to the head of B, vector B, that's called the summation of vector. Let's use another color. That's the summation. This summation also has another name, which we called it resultant vector. Resultant vector. Then vector R is the resultant of vector A and B. Means addition of vectors. We add them. And this method that I use head to tail, maybe these 2 vectors, maybe 3 vectors, maybe 4 vectors, doesn't matter how many vectors. You can add head to tail, head to tail, head to tail, and then the first tail to the last head shows the resultant. This is triangle method. Triangle method. Okay. What is parallelogram method? Parallelogram method, again, assume A and B are free vectors. I draw from a point, that's the 6-inch vector A, this is 9-inch. 9-inch vector, I draw vector with equal to A and parallel to the original, because it is a free vector. A free vector is a vector that you can move it in its plane, and line of action is always parallel. Doesn't matter it is where, to the original line of action. It can move everywhere with one condition only, that is parallel to the original configuration. We called it what? Free vector. And then from point O that I draw vector A, I draw vector B as well, which is 8 inches, parallel to B and equal to B is vector B. Then, if you construct a parallelogram based on A and B as the 2 sides of a parallelogram, then let's construct it. Here draw a line parallel to B, here draw a line parallel to A. Then I construct a parallelogram. Then the diagonal that starts from the shared tail, we got it what? Shared tail. The diagonal that starts with the shared tail is the resultant or addition or summation of these 2 vectors. So here the draw this diagonal. That shared tail vector, we called it resultant, exactly equal to this one. This is called parallelogram law. Triangular law, or say, you can call it law as well. Which law you are using, triangle or parallelogram, to find the summation of two vectors. That's the summation of two vectors. We use this summation to find the difference, subtractions of two vectors. Okay, how? Let's know what is parallelogram law. Use again. Parallelogram law or triangle method is also used for subtraction of vectors. Before I talked about subtraction of vectors, let's I talk about the multiplication of a scalar by a scalar. Assume that we wanted to multiply a vector by a scalar, by a number. For example, if I wanted to multiply 2 by vector A, what is it? If you multiply a scalar into by a vector or vector by a scalar, the result is a vector. It has the same sense of direction, and its magnitude is equal to that number times the magnitude of that vector. Okay, magnitude of 2A is equal to 2 times A, or 2A. Double. This is A. How much is it? A is equal to 9 inches. It's a free vector. I draw 9 inches. This is vector A. And if I multiply by 2, is another vector which has how much? 18. It means 11. That's the 2A. I multiply this vector by 2. Okay? Then the resistance is the same. Direction is the same. Magnitude are double because I multiply by 2. If I multiply by 3, magnitude is 3 times larger, or 4 times larger. What happens if this is, we have a negative number? If I multiply the vector by a negative number. Okay, assume that I multiply vector by negative number, which is -1, for example. I multiply -1 by vector A. The result is a vector. The result is a vector that magnitude is the same because you multiply it by 1. And direction is completely opposite to that. Assume that if this is A, then this is -1 times A, or we call it minus A. The vector equal to the same vector you multiply by negative numbers, for example, -1, and then the direction is opposite, sense is opposite. That's the difference. If you multiply a vector by a negative number, if this negative number is -2 or -3, the magnitude is 2 times and 3 times. The only thing that is changed is direction of the vectors, which is opposite to the initial vector. Okay, let's use this definition that we made here for subtraction of vectors. Then we learn here, if I have a vector C here, then minus C is this one. Vector C, the same magnitude and but different direction. Okay, then we know if we have vector C, what does mean vector minus C vector? We have vector A, what does mean minus A? If we have vector B, what does mean minus B? Just a vector, the same direction, the same line of action, for example. If it is a free vector, it doesn't matter. And the line of action is just parallel. Line of action is just parallel. Then let's consider we have a A and B, and we wanted to consider the A minus B, vector A minus vector B. Let's do some writing here. I can write it A plus minus B vector. because minus b vector is another vector. You can call it vector c. Okay? Then, instead of I subtract a minus b, I can change it to an addition, a plus minus b. What is minus b? Minus b is this one. Let's add these two, a and minus b together. Okay. I draw parallel to a and 9. This is a, vector a. And triangular along use minus b added tail to tail is 8 minus b. I just add a to vector minus b. And tail of first, head of the last is showed the addition, and in the other way, subtraction. This is vector a plus minus b, that we can write it minus b. That's a resultant of a minus b here. From one some point of view, this is the addition, because I add a to another vector, which the name is minus b. You can call minus b another vector, which is c, called minus b equal to c. Okay? You can call it vector c. Then I add a to vector c. If I wanted to use it as a parallelogram law, okay, I draw free vector a again, free vector a, parallel to a, and from we just shade the tail, draw minus b here, which is 8, or c, parallel to minus b, vector c, which is equal to minus b. Then construct the parallelogram, and the resultant of this addition is the diagonal that has the shade tail. From shade tail, diagonal, consider diagonal that has the shade tail with the other vectors on top. This is a plus c, which is equivalent to a minus b, because c is equal to minus b, equivalent. Then this is the subtraction. Actually, when you add two vectors a and b, the other diagonal shows you the other diagonal, smaller one, shows the subtraction. Okay? Parallelogram law. This is addition and subtraction of two vectors. And multiplication of a vector by a negative number and a scalar, you saw that. And we have here the resultant, the resultant of two vectors. And there is another definition here. When we have the resultant, vector r, resultant vector r, these two vectors are called component of this vector. Components of vector. Components of vector are vectors A and vector B. A and B are called component of vector R. Component means if we add them together, we get the first vector. If two vectors are say that, well, okay, we are component of this vector, it means that if we add them together, we find that vector, the resultant vector. Okay. If you have the resultant of two vectors, and you wanted to find that two vectors. And you know the direction, you know the line of actions of the components, but you don't know the magnitude and directions. You know just line of actions. For example, assume that we have a vector, resultant vector v, vector v. We wanted to find its component along two direction. We say that resolve this vector into two components in these two directions, or decompose these vectors along these two directions. How we do that? You have to find tail of this vector, consider the tail of this vector as point O, and draw two lines parallel to these directions. One line here, let's say show them in different color. Line parallel to this one, and a line parallel to this one. And from the head of the vector, draw two lines parallel to this direction as well. Then these two vectors, we show them by dash line, and later I say why I show them with dash line. These are called components of vector v. Components. You can call them vector A, and this one vector B. Okay? Then we can resolve or decompose. Resolve or decompose any vectors to two vectors into different direction. And these two are components of vector v. Then you know what is mean components of a vector, what does it mean resolving or decomposing of a vector, and what does mean resultant of two vectors. Okay, let's go a little further because we work in the system frame coordinates, and the most important one is the rectangular coordinates, that these two lines are perpendicular together. Before that, I talk about projection of a vector in onto a line, projection of a vector onto a line. See what does mean projection. If you had engineering drawing, you know what does mean orthogonal projection. Assume that again, we have another vector, vector S, and I wanted to find its projection about an axis or a line like direction like W or U, like this direction. From tail of the vector and head of the vector, I draw two lines orthogonal, perpendicular to this direction U. These are called projection line. This is orthogonal projection. We can project in any directions, not 90 degrees, but in a static, we use 90 degrees only. Here, to find projection. These vectors that I show it here with dash line again, I explain this dash line as well. We call this vector, for example, V is the projection of vector S on direction of U. Why I show it with dash? I promise you that, talk about it. Dash means that one of these two exists. They couldn't exist at the same time. When a vector, a force is a vector acting on a body in any direction, and you resolve it into two components, this force and this force, then you must select the body V is acting on the body or its component acting on the body. You don't have three vectors here. That's important that we show them with dash. Dash means you must consider this two or consider this one solid line. You have to consider this vector, that this force that acting on a body object, or these two acting. They cannot be together because this force is resolved into its components. And when the components exist, the force doesn't exist anymore. This is why we draw a line like this, that it means that this doesn't exist anymore. And these two represent the force. And the original representation resolved and doesn't exist anymore. That's it. Projection also is like that. It doesn't mean actually that S doesn't exist here. Just shows the projection that I project this vector onto this direction. What's the use of that? To find the components in orthogonal coordinates. Well, how much is it, the projection length? If I draw a line here, if I draw a line parallel to the original vector, if we find the angle between the vector and direction u, we call it theta, angle theta. And we can show it, prove it, that this length is equal to, from triangle, from definition of sine and cosine, we can find that magnitude of this time is equal to the magnitude of this, because equal to magnitude of letter S times cos of angle between them, cos theta. Or you can say magnitude of V, which we show easily by E, simply by E, and magnitude of S we show as cos theta. That's the relation between a vector and its projection on any direction. You can project a vector in many directions. Okay, have it here. We wanted to go to the next step, which means resolve a vector in Cartesian coordinate or rectangular coordinate, that the axes are perpendicular together. Axes are perpendicular. Okay. First, we consider two-dimensional, that we have only x and y axis in a plane. That's x, that's y. And then consider a free vector v. Here, I wanted to find the resolve this vector into these directions, decompose it, or find its projection onto this axis. Okay, this is a free vector. I can draw it from the origin of the coordinate. The free vector is parallel to the original and is equal to that. What is it? 12 inches. 12 inches parallel. This is vector v. Angle between this vector and x-axis, we call it theta. And I found the projection, draw two projectile lines. This is called orthogonal projection because the projectile line is perpendicular to the axis, 90 degrees angle. And this length, if we call it, this length is a vector, and this one is another vector in y direction. We call the y component of v an x component of v. We show it with vx vector, and this one v and this y vector. Okay. Vx vector and vy vector. This Vx, you can show the magnitude of Vx. Sorry about the noise. And magnitude of Vy is called Vy. Simply Vy. Okay. Here I wanted to introduce two unit vectors, which is important. And from now till the end of the static and dynamic lessons, we use them. Unit vector I, which is a hat, and unit vector J in direction of Y. Unit vector I and unit vector J. What is it? This unit vector direction is direction of positive X. Then I magnitude, you know that, is 1. I direction is the same as positive X. J direction is the same as positive Y. Later, when we consider the three-dimensional frame, orthogonal frame, we have another unit vector which is called K and is in the positive direction of axis Z. Okay, but because everything is in the one surface, one plane, we just consider 2D, two-dimension. And any vector which is in x direction can be shown by a number, a scalar, and a unit vector r. It means that Vx here Vx vector is the component of vector v in direction of x is equal to magnitude of Vx, which is Vx, times unit vector I. This is a number. This is a value, like 5, 6, 12. And Vy vector is equal to magnitude of Vy, which we show Vy, in direction of J. It means that from now on till the end of the course, static and dynamic, we use I and J unit vectors. Just multiplication by a number. Number times a vector is a vector. The magnitude, how much? Vx depends on the amount of Vx. Vy. The direction is the same as the vector I. Vector. That's it. And if we wanted to show it, we show summation of vector Vx I plus Vy J. Vx, and Vy are the components, orthogonal components of vector V in x and y coordinates. And how much the magnitude? Use the projection, the relation between the hypotenuse and side that is opposite to theta and side which is adjacent to theta. Side that is opposite and side that is adjacent to theta. How much is Vx is equal to magnitude of V whole vector times cos theta. Let's stick to this cosine of theta, because some confusion happens if you, for example, show the angle with respect to y-axis. Then in this case, sine and cosine places will be changed. Then we show only the angle of vector with respect to x as theta, and we stick that always Vx is equal to the magnitude of the vector times cosine theta, and Vy is the magnitude of the vector sine theta. If you change this angle, for example, consider this angle alpha, then this definition will be different. Vx is equal to V sine alpha, and Vy is equal to V cosine alpha. Because I don't want to I had this experience when I marking the exam paper. I see that the confusion happen. Which one is multiplied by sine and which one must be multiplied by cosine? This is why I just stick to this one that show the angle only between the vector and the x-axis and follow only these two shapes, Vx cos theta, Vy sine theta times the magnitude of the original vector V. After you became expert by practice and practice and practice, you can just call alpha here, show this angle here, or show this angle, and then you never make a mistake. That which one was sine, which one was cosine. Okay? Then here, for the first time at the initial, stick to this shape that measure or find the angle between the vector and x-axis and follow these two. We can write this summation in another form that is equal to V cos theta I and V sine theta j. That's another form. V is the magnitude of vector V. Cos is the angle between vector V and x-axis. I is the unit vector direction of x, and j is the unit vector direction of y. Okay, thank you for watching, and see you in the next video.